I'm delighted to introduce our keynote speaker, Costis Maglaras, Dean of Columbia Business School. He joined Columbia in 1998 when he became part of the Decision, Risk, and Operations Division. Prior to becoming Dean, he served as chair of the Decision, Risk, and Operations Division at the Business School and director of the school's doctoral program, and was a member of the executive committee of the university's Data Science Institute. His research lies on the interface between applied mathematics, economics, and engineering, with emphasis on stochastic networks, financial engineering, and algorithmic pricing and revenue management. Outside of the business school, his experience is focused on financial technology, asset management and markets, and digital technology. In the last decade, he has worked with major financial institutions and hedge funds, including long-standing collaboration with Goldman Sachs, Global Markets Division, focusing on quantitative research and equity trading. His keynote, entitled AI, Growth and Productivity, is sure to be instructive as we consider the role of AI in our lives today and into the future. Costis, thank you for joining us in Tokyo, and please join me in welcoming Dean Maglaras to the stage.
Thank you, David. Thank you all for coming. Thank you for this wonderful event and for your support. I want to make two quick comments before I dive into my presentation. The first thing is that CJEB, that you have all being part of for quite some time, is a gem at the school. It has been a gem since 1986, building on the leadership of Hugh, Patrick, and now under the leadership of David. It continues to be an area that we're proud of, an area where incredibly strong work, an area where we have really strong ties between Columbia University and Japan, which is something unique as we were talking about yesterday. David mentioned about Taka's recognition to be honored with the Order of the Sacred Treasure, gold race and neck ribbon. He omitted the fact that he himself got a recognition of the Order of the Rising Sun, gold race and neck ribbon. And the reason I'm mentioning all of this is to say that our directors are recognized for their deep scholarship, their commitment to education, and their sort of relentless pursuit to build strong ties between Columbia University and the business school, but the university at large, and Japan. And these two awards that both of them got is a recognition of all of these things simultaneously. And I think that's wonderful to see. Okay, so now I'm going to jump in, and I'm going to talk less about trade and productivity and growth. I'm going to talk a little bit about AI. Unlike many of you that are economists, I'm an electrical engineer. So, you know, if I wasn't the dean of the school, I would probably be sort of working on the science behind AI right now. So I'm going to give you a little bit of a bird's eye view, and then I'm going to talk a little bit about what I think may be happening in the future. And so the first thing is we talk about how fast AI is going to transform everything. I really want us to sort of reflect a little bit back and realize that it has been taking quite a long time to get to where we are right now. And I'll give you kind of a bit of an overview on that. But we have accelerated quite a bit over the last decade. And this level of acceleration is continuing as we speak. And we're going to then talk a little bit about some of the implications. So AI, the field of AI, was born in the 1950s. The term was coined in 1956. And a major thrust back then was to decide how to sort of create machines that can sort of do tasks that we humans perform. And there were two different ways of doing it. The first one, which we're all familiar with and in some sense dominated for half a century, is one where we would program computers rules, and it will say, if you see this, you do that. If you encounter something like that, then you sort of do something else. Now, the problem, and we all have our favorite things about rule-based systems, and I'm going to not talk much about it, but this became prevalent in the world since the 1960s, and they were prevalent, I would say, until about 15 years ago. And then, something happened. The second way of, now, one thing that we all know is it's very difficult to convey all of our knowledge into a rules-based system. And that's a bottleneck. The second way of actually building a machine to do what we can do is to feed the machine examples and teach it, okay? And hopefully the machine learns and generalizes from the knowledge that we give it, and then it performs some kind of task, okay? That was sort of essentially the start of what we call machine learning, all right? So AI that we talked about today is really the second approach, right? The machine learning approach. Now, it turns out this had started way back when, and it started by a gentleman called Rosenblatt in 1958 with his invention of something called the perceptron. Okay, so Rosenblatt actually built a machine to learn by example, to sort of recognize and perform some tasks, and created that machine about 65 years ago. And the basic of this machine, I'm going to show you some picture. So this is a very simple task here, and I'm going to try to teach the machine to decide whether something is a check mark or an X. So the first thing I'm going to do is I'm going to sort of basically digitize that information, all right? It's because computers need to process information in a digital form. So I'm going to take that picture, and I'm going to sort of convert it into numbers. And then I'm going to feed these numbers into the perceptron, okay? And the way Rosenblatt designed the perceptron is he says, I'm going to take each of these numbers. So this is a picture of a check mark, let's say, in that case. And I'm going to take all of these numbers, and I'm going to multiply them by a set of weights or parameters, okay? And then I would look at the outcome of that, and if the outcome is, let's say, large and positive, I'm going to declare that I get some result, and if it's sort of negative, I'm going to declare that I have a slightly different result. This was the basis of the machine. So, but the idea here is more general. So I take information, I digitize it, okay? Then I have a set of parameters or a model that combines this digital information, in this particular case, by just literally multiplying them, okay? And then I use that outcome to make a decision. Is that a check mark? Is that an X? Is it a dog? Is it an airplane? Is it a, and et cetera, okay? So that is the basis of these algorithms. And that machine, as we said, existed back then. And what you do is you feed it a lot of examples, okay? You take a lot of pictures, you digitize them, you then feed them through the network, you look at which is wrong and what is right, and then you start tweaking these parameters, okay? We've all heard how much time it takes to train these neural networks in these large language models. That's what they're doing. They're feeding examples, right? The machines, the neural networks, the large language models are huge machines, and we're going to talk about that in later on. But you feed them examples, and then you tweak the parameters so that you do well based on the input data and the outcome, the label data that you have in there. And that's the basis of training a neural network, okay? All of that existed in 1958. So unfortunately, it didn't go very far. It kind of almost died a few years later, and it kind of stayed dormant for a very long time. And the reason for that was that a person that was a professor, Rosenblatt was at Cornell, Minsky was at MIT, And Minsky said, listen, this idea that Rosenblatt has, we're only going to work very simple examples, very structured environments. And most real-life examples are a little bit more unstructured, and it's going to fail. And that sort of essentially blew the Rosenblatt approach and sort of made it dormant for 25 years. Interestingly enough, Marvin and Rosenblatt were high school classmates at Bronx Science in New York. But that comment by Minsky sort of literally killed Rosenblatt's academic career back then. That's a little bit factoid. So it turns out Rosenblatt had actually thought of the solution. He had said, the structure that I've been able to build is very simple, and maybe what you need to do is build a network, like something that has multiple stages. But he couldn't do it. He couldn't build a machine to do it. So that stayed dormant until the 1980s, okay? In the 1980s, it was the next invention that took place. That's a very simple idea that we all learn in calculus when we are at school, and it's called backpropagation. So the whole idea is, I'm going to feed you a picture, you're going to compute whether it's a check mark or an X, and then I'm going to look at whether that's right or wrong. If it's wrong, I want to take that information and tweak my parameters. And the way I'm going to do it, I'm going to backpropagate that information through the network. Okay? So I start from the very end where I realize that I made a mistake, and then I use that information to start propagating back through the network. Okay? It's called the chain rule in calculus, if you remember. And then eventually I train the network. So that idea was invented in the 1980s, and we were ready for business, so to speak. And it turns out it didn't go very far, okay? It lay dormant after that for about 20 years. I entered grad school to study electrical engineering exactly at that time, in the so-called second AI winter. At that point in time, everybody thought that this field is dead, okay? I took courses in neural networks in 1990, and it was more like talking about an sort of old field that proved unsuccessful. And the reason it was dead, or it couldn't proceed, is we didn't have fast computers, and we didn't have abundant data, okay? And that was the case until a hardware solution came about. And in particular, we started having very fast computers, and more to the point, we started having something called the GPU, Graphical Processing Unit, originally designed to do graphics in our sort of Windows operating system machines, then to play video games, then to mine Bitcoin, but eventually to train neural networks, okay? That was a hugely important bit that allowed for this sort of explosion of AI, which now I'm going to focus on in more detail. I'm going to sort of sidestep, and I'm going to say that I've had wonderful discussions over the last 2 days here in Tokyo, and in particular, a lot of them mentioning the semiconductor industry and sort of the opportunity that exists here to really be a leader in that space. So I think that's important. So what's going on? Why is it moving so fast? So I think things are legitimately growing exponentially. And if you draw an exponential curve and you compare it to sort of much more pedantic linear curve, early on the linear curve will look like it's doing better than the exponential curve until it gets overtaken. And when it gets overtaken, it starts getting increasingly overtaken by that because the exponential curve grows very fast. And I'm going to show you some pictures to just make that real, because the picture that I just graphed right now, it's really not that important. So this is all data about investment in AI startups, okay? And you can look at the x-axis, it says 2010 to 2014, okay? So it was growing, but these numbers are like pathetically small. The highest number is 300 million. At some point in time last year, you were spending 300 million a day, not a year, in investments in that space. But here's what happened over the next, something important happened, by the way, in 2012-13. This is the demonstration that a neural network started being better than any machine in doing image recognition. Okay, that was a watershed point. It's called AlexNet. Okay, and that was sort of a point where suddenly the focus from researchers moved away from machine learning to neural networks. Okay, and this is when the venture capital industry, in particular, most of it in the United States, started focusing, and it started investing more. That's next year. That's how an exponential looks. Okay, that's the year after that, and I'm not going to show you anything more, but that's like suddenly people realize that this technology has incredible potential, and sort of a lot of money poured into it. Okay, so exponential amount of resources being invested to research these technologies. That's point number one. The next thing is Moore's law, okay? So we have all may have heard about that. That talks about how chips become sort of increasingly powerful in a way that grows exponentially with time. So this is in logarithmic scale. So if you look at the scale, these are powers of 10, powers of 100 to be precise, okay? And this is time. It's not important to look at all of these, but if you were to look at how much progress we have made in the last 30 years, okay, chips have become 1 billion times faster or more efficient over the span of 3 decades. Okay, there are not that many things that become 1 billion times better in 30 years. Our cars haven't even become 100 times better, 10 times better. They drive at the same speed now than they were driving 30 years ago, okay? The chip is 1 billion times faster. That's normalized per dollar spent. For every dollar that you spend, okay, right, a dollar that you spend in 1990 versus the same dollar being spent right now you're doing 1 billion times more calculations per dollar spent, okay? So that's, our computers are becoming exponentially more powerful, okay? This is what the exponential looks like. So this is 2012 at the bottom, the knee of the curve, okay? This is actual data, all right? And this is where we were at 2022. Which, by the way, by 2012, we thought we were pretty good in terms of our computing ability. And when you plot it like this, it looks like we were in the Stone Age, okay? And if we go forward by 10 years, it will look like 2022, we were on the Stone Age, if the exponential continues. So this is how fast our ability to compute is moving, okay? The next thing that I want you to know, and this has 2 implications, is that we have become a lot more efficient in compute per kilowatt hour, okay? So as we plug our computer into plug it into the wall and we start sucking electricity, we can do a lot more calculations per kilowatt hour, okay? But what's important, if you look at this graph and you look at how much better have we become over the span of 30 years, it's about 10 million times better. Okay? So if you spend 1 kilowatt hour now versus 30 years ago, I can do 10 million times more things today. But I just mentioned 5 slides ago that I can do 1 billion times more calculations per dollar, okay? So it turns out I'm actually spending a lot more electricity right now, 100 times more electricity right now than I was spending 30 years ago. Because I can do 1 billion times more, but per kilowatt hour, I can only do 10 million times more. So I actually spending a lot more kilowatt hours, and this is why our data centers are using exponentially growing amount of energy. And this is something for all of us to grapple with in the future. So, we're getting very efficient in terms of power, but still we're getting so much more efficient in terms of compute that we're actually spending a lot more power, okay? So that's something to remember. So this is something about data. So this is a graph about cameras. And of course, a lot of them are coming from the beautiful country of Japan, right? But this is about camera production, and this is how it has grown over time. And it looks like I messed up the slide because it's truncated, okay? And the reason it's truncated is because the real slide looks like this, okay? Exponential, all right? That's how an exponential looks. So exponentially faster computers, exponentially more data feeding the computers. And the last thing that I want to say is that, I'm going to skip that slide. I'm going to focus on that one. This slide talks about the size of the neural network, or the size of the brain that I'm estimating, I'm training, as a function of time. And if you look at the scale, at the very top it says 1 trillion parameters, okay? So complicated, sort of state-of-the-art neural networks right now have a few trillion parameters. The picture of Rosenblatt's that I showed you had about a dozen, okay? So now we're training something that has 1 trillion numbers, and I'm tweaking these trillion numbers to make it ever more efficient. So where are we? We have, and that's how neural networks look, okay? So we're investing a lot of money in AI, as we should. Our ability to compute is increasing exponentially fast at constant dollars, okay? We're getting exponentially more efficient per kilowatt hour in our ability to compute, but we said that there is a small difference there, and that has sort of energy implications that we all understand. So exponentially faster computers, exponentially more data feeding the neural networks that we're training, and the size of the brains, the size of the neural networks that we're estimating, that we're training, is itself growing exponentially fast. So we're training exponentially bigger brains with exponentially more data on exponentially faster computers, and this is what has been happening for the last sort of decade or so, okay? And incredible things happen at the end. All right? And this is why all of these things are happening. So, we talked about data, image, and video. So one comment is, are we going to be overtaken by machines and what's going on? So we have one advantage as human beings, okay? And one, our strong advantage is we're low power. We don't lose a lot of power in order to operate. And that's important. Right? We can drive a car and consume 20 watts of power. Whereas if you go into a self-driving car, you have almost a supercomputer in the trunk, okay? And you have sensors everywhere, and you're consuming about 1,000 times more power in order to do what we do while we're talking to a friend, having a phone conversation, drinking coffee and driving with one, so that we're a lot more power efficient, which is our edge. Maybe the only edge we have for now, okay? But we'll keep it. So I do believe that there are a few factors that are going to have dramatic implication in society. AI is one of them, okay? But it's not the only thing that is driving change, but it's one of the big ones. And we need to be both concerned and in tune with that. So now I'm going to talk about a few thoughts about the future, and then I'm going to try to wrap up, okay? So I want to start by giving you an anecdote about productivity. Given the fact that I'm not going to talk a lot about productivity, I'm going to tell you a story. So 2 years ago, or a year and a half ago, I was preparing to do a small briefing to my board at the business school. And my daughter, who is 15 years old at that point in time, was a good programmer, was sitting around doing nothing. It was Christmas break. So I told her, it's like, why don't you write some code for me in Python, just for fun, and go and download the transcripts of the earnings calls of every company in the S&P 500 in the year of 2022, and look for the term AI or artificial intelligence or machine learning, and tell me what fraction of them we're talking about. Dad, what is, and transcript, what's an earnings call, 5 minutes, this is fine. So she didn't do it, okay? So I opened my laptop. That was December of 2022. That was like 4 weeks after ChatGPT came out. And I said, okay, let's try the following. So I wrote in ChatGPT, write some Python code, blah, 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 to do this. I wrote exactly what I told her. Press return. 20 seconds later, I have 4 pages of Python code. Okay? It has like a few typos. If you know anything about Python, you could correct these typos very quickly. And the code essentially was running. Okay? That's my productivity anecdote. Like, if we will be able to use these machines to sort of really be a lot more effective, fast in our work. And this is already happening in programming. People say that overall, people that use large language models to sort of sketch out code and then they adjust that code, they see 10 to 20% productivity gains in software engineering. So that's like a simple thing and an important thing, however, okay? The other thing is an example from call centers. So we can use large language models to both try to answer questions that people have, and also sort of design the paragraphs that somebody's reading to you when they're talking to you on the phone. And it turns out that leads to sort of significant improvements in performance, successful resolution of questions, etc. Okay? So that's a very simple application of a large language model. Okay? So we're already seeing that in the data, and it's very early stages in our ability. At some point in time, we're going to talk about work substitution, and call centers is top of mind for me. But what are we going to do now? What's the state of play with generative AI, and where are we focusing on as researchers and also in deployment? So the first thing is, a lot of these large language models that we use are sort of what I would call general purpose models, okay? Companies, what they could do is they could sort of post-train these models using proprietary data. And this is an area where, there's a lot of value add to be derived. And you can think of it in finance, you can think of it in other areas. This is sort of something that we're seeing, and we're seeing new applications on a weekly basis. The models that we have designed, as I said before, are very large, okay? There is a lot of work that is happening right now on whether, rather than having very large general purpose models, whether I can create smaller models that are sort of fit to purpose. They're only going to be doing one thing or 3 things, not everything, but maybe they can be much smaller. And if they are much smaller, right, maybe they can fit on my phone. All right? So there are like 100 companies that have been funded in Silicon Valley right now trying to build neural networks, large language models, but not so large so that they can fit on your phone. Because it turns out a 1 trillion parameter model doesn't fit on your phone. Okay? But a 1 billion parameter model does fit on your phone. So that's where a lot of focus is going on. We mentioned about AI, this general purpose model. We're all business people in here, And I think an area that we're going to sort of start to see quite a bit of work is actually training these models with the intent to actually optimize or improve business decisions. Right now, these models are being trained to really generate text, okay? But we're using them to make business decisions. So maybe when I generate text to send an ad to Mr. Mogi here in the audience to have him click and buy my product, right? I should train the model, taking into account whether Mr. Mogi bought the product or not, okay? Or from previous interactions, rather than just train a model to just write beautiful text, okay? So we're going to be seeing business objective functions entering the training of these models to make them more effective or efficient. We talked about augmentation, okay? Task automation and speed of adoption. So I want to I'm going to say one more story, and then I'm going to show a picture about some other comments that I think are pertinent to Japan, and skip through some slides. So the other story is about speed of adoption. How fast are we going to be sort of seeing that in practice, okay? And the story that I have is the following. In 2000, all of us had internet accounts. All of us had computers at home. Every bank had very powerful computers. We could have been ready in 2000 to completely switch to online banking, but we didn't. It took about 20 years for that to happen in the United States, and I imagine similarly in Japan, okay? So it takes time for these changes to sort of dramatically change old processes. So, you know, even though the technology is sort of moving very fast, it's going to take time for dramatic disruption in large areas. You know, startups will be innovating, but in large areas, it's going to take some time. So I had some slides about what jobs maybe get automated versus not, and I'm not going to talk through them. They're in your packet, but probably incomprehensible. But I want to say something about robotics, because that's an area where Japan is sort of one of the leaders in the world. And I think robotics is going to be transformed over the next decade or more. And AI will have a big implication. And I imagine that that's an area that Japan can lead globally with proper investments. Now, what is AI going to do? So in some sense, robotics are extremely effective in doing jobs in structured environments, you know, like in factory floors where, you know, you're picking up things, you're sort of bolting things, you're moving things around. And the future is about much more accurate modeling of the physics of the world, okay? So that's one thing. The next thing is much sort of better ability of touching things and moving things and controlling things, all right? Dexterous robotics. And then over time, it's going to be sort of a dramatic increase of ability in our robots in order to be able to perform in unstructured environments. Okay, we may have robots in our houses. They may be cooking for us. We certainly have robots that can move around and drive us around. I don't know how many of you have been in a truly self-driving car. It's great. I did it in San Francisco. You call a car, and a car shows up, and there's nobody in there. Okay, so it's sort of unnerving. And then you open the door, you get in, and then it drives off. And you know, it drove me for an hour in San Francisco. Okay, and dropped me off, and I went to a reception with the president of the university. And I was just like, wow. You know, this is like an incredible engineering feat. So there's going to be a lot. But to do that, that's a robot, right? That's a robot that moves, that thinks, that can see, it can sense, and it can compute things. So this is the future of robotics, and I think that's an opportunity in the context of where we're at. Okay? So there are unintended consequences of robotics and of AI, and we need to be cognizant, and I'm going to stop. Okay? All right?